Let me just review very quickly what we've done from the beginning. So here are two homework problems on second order linear ordinary differential equations with constant coefficients and homogeneous. So in the homework assignment, problem 11, 2y double prime plus 3y prime equals 0, the first thing we did was divide by 2, put it in the standard form where the coefficient of y double prime is 1. And we worked out a solution, including, these are initial value problems. So after we have here the general solution, you find the values of the constants C1 and C2, which satisfy the initial condition, and this is what we got. In problem 14, we had this second order equation in the right form, A is equal to 4, B is equal to 5. So in this case, the discriminant is negative, so we're going to get fundamental solutions that involve the cosine and the sine. And this is the general solution. And we have to do a little bit of algebra, high school algebra type. To compute the coefficients C1 and C2. And when we do, they're each equal to 2, and we found the solution. Okay. So on page 312, number 13 is something called Bernoulli's equation. And the important thing about Bernoulli's equation is it is nonlinear. So Bernoulli's equation has the form, it's a first order differential equation, y prime plus p of xy equals, now if we're just equal to a function q of x, this would be a non-homogeneous linear equation. But it's q of x y to a power n. If n were 0, that would just be 1. If n were 1, this would just be y. We would bring this term over to the other side. But if n is different from 0 or 1, we now have a truly nonlinear equation. And someone, maybe it was Bernoulli, discovered a way to transform this nonlinear equation to a linear equation. And the corresponding linear equation, and we're going to show an equivalence between these two, is y prime plus k times p of x, y, equals k times q of x, where k is equal to 1 minus n. And because n is not equal to 1, we know this is a non-zero constant. In fact, we know it's not equal to 0, and it's also not equal to 1. And this equation is linear. So in problem 13, we're asked to prove that every solution of this equation gives a solution of this equation, and conversely, every equation of this equation gives a solution of the nonlinear equation. And maybe just to use the same notation that the book uses, here I'm just going to call the unknown function v. So we want to prove that y, a function y, is a solution of this equation. I'll call this equation 1. If and only if I let v equal to y to the k, this is the k, is the solution of 2. Okay. So what this says, what we have to prove is the following, that if y solves this equation, then v equal y to the k solves this equation. And conversely, if v solves this equation, and then the kth root of v solves this equation. So here's how you prove it. So you have to prove, there are two different things to prove. So suppose y is a solution of equation 1. This is equation 1. Let v equal y to the k. All right. Is there any questions so far about what I'm doing? I haven't started. I'm just about to start. But this is just setting up the problem, stating so that the problem is clear. So if v is y to the k, by the chain rule, v prime is k y to the k minus 1. So v prime plus k p of x v oops, just 1 second, please. Sorry, ready to start? So v prime plus k p of x times v, this is what v prime is, k y to the k minus 1, plus k p of x times v, which is y to the k. Now I can factor something out of that. Oops, I'm sorry, I made a mistake. So v is, when I differentiate v, it's k y to the k minus 1 times y prime. That's the chain rule. So I can factor ky to the k minus 1 out of this, and I'm left with y prime plus p of x y. But y is the solution of this differential equation. So this is equal to ky to the k minus 1 times q of x y to the n. Which is k q of x y to the n plus k minus 1. But k is 1 minus n. So n plus k minus 1 is 0. This is k q of x y to the 0, which is k q of x. Perfect. So if y is the solution of this nonlinear equation, the Bernoulli equation, and we let v equal y to the k, then v is the solution of this linear equation. That's what we just proved. Let's see if I can prove the second half in the same space. So suppose v is a solution of, suppose v is a solution of v prime plus k p of x v is k q of x. And I let v equal to y to the k. So v prime is k y to the k minus 1 y prime. So v prime plus k p of x v is v prime k y to the k minus 1 y prime plus k p of x times v, which is y to the k. Factor out k y to the k minus 1, I get y prime plus p of x y. But v prime plus k p of x v, this is k q of x. Let me do it on the, do it again because I need more space than I. So v prime is a solution of the linear equation v prime plus k p of x v equals k q of x. Suppose we let v equal y to the k. Where k is equal to 1 minus n. So v prime plus k p of x v, v prime is k y to the k minus 1 y prime plus k p of x v, which is y to the k. If you factor out k y to the k minus 1, you get y prime plus p of x y. Of course, v prime plus k p of x v is equal to k q of x, equals k q of x. You can divide by k because it's non-zero. Bring this to the other side, y prime plus p of x y is q of x y to the 1 minus k, which is q of x y to the n. So that's the proof. You can reduce every Bernoulli equation, every nonlinear Bernoulli equation, to a linear equation. And that's problem 13. And problem 14 is an example. So problem 14 is solve the equation y double prime minus 4y equals 2e to the x, y to the 1/2 on the interval from minus infinity to infinity. And we want to solve the initial value condition, y of 0 is equal to 2. So this is my nonlinear Bernoulli equation. This exponent, n, is equal to 1/2. So k, which is 1 minus n, is 1 minus 1/2, which is also 1/2. My function p of x is minus 4. My function q of x is 2e to the x. Okay? So we transform this Bernoulli equation into the equation v prime plus k p of x. What is k? 1/2 times p of x, which is minus 4v prime, minus 4v, which is v prime minus 2v, equals k q of x. K q of x is 1/2, 2e to the x is e to the x. So we've reduced this nonlinear equation to this linear equation. Questions so far? I assume the fact that there's no questions means that this is impossibly difficult. But this is just, now we've reduced it to just the usual first order linear equation. And we know how to solve them. Remember, if you have let's just recall. If you have the equation v prime plus p of x v equals q of x, we have the function a of x, which is integral from 0 to x, p of x dx. P of x is minus 4. Sorry. P of x is minus 2. It's minus 2x. And our solution is v of x equals some constant b, e to the minus 2x, plus e to the minus 2x times the integral from 0 to x of the function q of t. Q of t, that's this function, e to the t times e to the minus 2t dt. This is e to the minus t. The integral of e to the minus t from 0 to x is minus e to the minus x from 0 to x is 1 minus e to the minus x. Should be a plus. And b, well, let's see. Let me just write it. So this is b e to the minus 2x. No. When we make our transformation from y to v, v is y to the k, which is y to the 1/2 or the square root of y. So v at 0 is the square root of y at 0. That's the square root of 2. So this b is the square root of 2. So v of x is the square root of 2 e to the minus 2x plus e to the minus 2x minus e to the minus x, e to the 2x. I keep putting these, this is always a plus 2x. E to the 2x plus e to the 2x minus e to the x. So that's square root of 2 plus 1, e to the 2x minus e to the x. That's the solution of this equation. And the solution of the Bernoulli equation that we want, it's v equals y to the k. So square root of y is v, which is root 2 plus 1 e to the 2x minus e to the x. So y is the square root of root 2 plus 1 e to the 2x minus e to the x. Now, this is what we have. Any questions? Now, okay, so before I do what is really the lesson for the day, which is to go from homogeneous linear equations of second order with constant coefficients to non-homogeneous equations, I want to emphasize something or remind you of something that I posted on Blackboard and sent an email out about last night, which is Maple. So there is a computer program called Maple. And they seem to come out with a revised version every year. So the current version is Maple 2020. And you need to get this computer program. You do not need to buy it because CUNY has a site license, has a license with Maple that we can provide Maple to all our students for free. So there is a eCUNY website where you go, you sign in as a student, and you can download various pieces of software, and one of them is Maple. When you go to the website, there's probably some sort of code there because when you actually start the download, it asks you for a purchase code, and CUNY has it for you. I mean, it's there. You just have to notice it. So if you've never used Maple before, that's no problem. I'm going to spend the class in a couple of weeks teaching you how to use Maple. If you're lucky, you took calculus at Lehman where we require a calculus lab, and most people use Maple for their calculus lab. But in any case, you're going to learn Maple because Maple has a simple program for solving differential equations. And it's always the case that the simplest equations, like the ones I just did, even though they may not look simple, the simplest equations are the only ones you can solve by hand, but many equations that come up in applications and come up in more advanced mathematics can't be solved by hand, and you need a computer to solve them for you. You don't have to write the program to solve the equation. That's all built into the software. So I'm sort of curious, just indicate by saying so or on the chat whether or not you have previously used the Maple software. Yes, no, anybody?
No, I've never used it before.
Okay.
I got a little experience. Yeah.
So it's an important thing to know. And just in general in the world, the more computer programs you know, the better prepared you are for work. Okay. So in the Apostle Notes, I scanned and emailed out some notes just before class started, and I also posted them on Blackboard. So this is in the notes, starting on page 329, section 8.15. This is non-homogeneous. Linear equations with constant coefficients. So the homogeneous equation with constant coefficients of order 2, y double prime plus ay prime plus by equals 0. And when it is non-homogeneous, there's on the right-hand side a function r. So r is some function which is continuous from minus infinity to infinity. So if we write the linear operator or the differential operator, L of y, this means for any function y, L of y is the function y double prime plus ay prime plus by. This equation means solve, find y where L of y is equal to r. Solve this equation. And it's a differential equation. It's an equation that involves a derivative. So it's a differential equation. It involves derivatives just of x. So it's an ordinary differential equation. And it's constant coefficients and yeah. Now, this is a linear operator. So we know that L of, if you take the sum of two functions, y1 plus y2, or even multiply those functions by constants, c1 and c2, this is c1 L of y1 plus c2 L of y2. So suppose L of y1 and L of y2 are equal to 0. That is, y1 and y2 are solutions of the homogeneous ordinary differential equation L of y equals 0. So then L of c1y1 plus c2y2, by this what we call linearity property, c1 L of y1 plus c2 L of y2, this is c1 times 0 plus c2 times 0, which is 0. So if y1 and y2 are solutions of the homogeneous equation, every linear combination of y1 and y2 also are solutions. Suppose y1 and y2 are solutions of the inhomogeneous equation, y double prime plus ay prime plus by equals r. So in that case, L of y2 minus y1, again, that's L of y2 minus L of y1, but these are both solutions of this equation. So L of y2 is equal to r, L of y1 is equal to r, so we get 0. So if y1 and y2 are solutions of the inhomogeneous equation, y2 minus y1 is a solution of the homogeneous equation. That v1 and v2 be the fundamental solutions of the homogeneous equation. So y2 minus y1 is some linear combination of v1 and v2. Every solution of the homogeneous equation is a linear combination of v1 and v2. If y and y2 are solutions of the non-homogeneous equation, then the difference solves the homogeneous equation, or in other words, y2 is equal to c1 v1 plus c2 v2 plus y1. So this is a very simple proof of a fundamental fact about linear equations. We call y1 is a particular solution of the ordinary differential equation. y1 plus c1 v1 plus c2 v2 is what we call the general solution of the equation. So if you have this non-homogeneous equation, to find all solutions, you only need to solve the homogeneous equation, which we know how to do, and find a particular solution of the non-homogeneous equation. And that gives us a solution, that gives us the general solution for the non-homogeneous equation. Okay. Someone says, can you use Maple to check if your homework is correct? The answer is yes. And actually, I keep meaning to post on Blackboard just solutions to all the problems that are in the book, that are in these apostle notes. I have to remember to do that this afternoon. But you can certainly use Maple to check your solutions to problems. Absolutely. On the exam, you're going to be asked to show your work as well as the answer. So if you have a problem on the exam and you plug it into Maple and you get the answer and write it down, that's not what I'm looking for, because I know in principle you can solve any ordinary differential equation with Maple. It's only if I see your work that I know that you actually have solved the problem yourself. Okay, so In order to solve the non-homogeneous equation, we need something which is called the Wronskian of two functions, v1 and v2. So the Wronskian, w of x, is v1 of x, v2 prime of x, minus v2 of x, v1 prime of x. And if you look at this expression, you might see that if you were to write down the 2 by 2 matrix, v1 of x, v1 prime of x, v2 of x, v2 prime of x, this is the determinant of this 2 by 2 matrix. So let's look at some examples. Suppose v1 of x is cosine kx, and v2 of x is sine of kx. Then v1 prime of x is minus k cosine kx. And v2 prime of x is v1 prime of x is minus k times the sine, and v2 prime is k times the cosine of kx. So the Wronskian of cosine kx comma sine kx is equal to this times this, k cosine squared of kx, minus this times this, minus times minus is plus, so I get plus k sine squared kx, which is k times cosine squared kx plus sine squared kx. This is 1, so we get k. So if k is different from 0, the Wronskian is different from 0. The Wronskian of the sine, cosine, and the sine. Let's take another example. Suppose we take exponentials. So what about the Wronskian of the functions e to the kx and e to the minus kx? So that's the determinant of, I have e to the kx, e to the minus kx. Differentiate, I get k e to the kx minus k e to the minus kx. The determinant is this times this minus k minus this, because the e to the kx and e to the minus kx cancel, minus k is minus 2kx. So if k is not 0, so these are really exponential functions, the Wronskian of e to the kx and e to the minus kx is not 0. That's very important because it means you can divide by the Wronskian. Okay, so here's the problem. Solve the non-homogeneous equation y double prime plus ay prime plus by equals some function r of x. So let v1 of x and v2 of x be the fundamental solutions of the homogeneous equation. Okay. So we're going to try to use a technique called variation of parameters to solve this equation. So we look for a solution of my differential equation of the following form. We're going to let y1 of x, a particular solution, be a certain linear combination of v1 of x and v2 of x, but not multiplying these by constants. That would just give us other solutions of the homogeneous equation. We want to see if we can find functions t1 and t2 of x, where what we get here solves the differential equation. So someone long ago, probably about 200 years ago, had the very clever idea of looking for something like this. And it turns out it works. And you let T1, I'm going to prove this, but the answer is T1 of x is going to be minus the integral of V2 of x, R of x over the Wronskian dx, and T2 of x is going to be the integral of V1 of x times R of x over the Wronskian. So what's going into this solution? I have my homogeneous equation. And there are two fundamental solutions, V1 and V2, which involve exponentials and trig functions. There's going to be a solution of the non-homogeneous equation of this form, T1 V1 plus T2 V2. And now T1 and T2 are functions. So R of x is the right-hand side of the equation. W of x is the Wronskian of the V1 and V2. And V1 and V2 are V1 and V2. So let me see why this works and how we get the right answer. So we have our differential operator, L of y is y double prime plus ay prime plus by. And our fundamental solutions of the homogeneous equation, we have L of v1 and L of v2 equals 0. And our problem is to find functions t1 of x and t2 of x such that L of t1 v1 plus t2 v2 is equal to R. That's the differential equation we're trying to solve. Okay. So we let y be this function t1 times v1 plus t2 times v2. If we differentiate, y prime is t1 prime v1 plus t1 v1 prime plus t2 prime v2 plus t2 v2 prime. We need the second derivative because this is a second order differential equation. So y double prime is, again, we're just using the product rule, is t1 double prime v1 plus t1 prime v1 prime. We differentiate this, we get t1 prime v1 prime. I already had 1, now I have 2, plus t1 v1 double prime. I differentiate this, t2 double prime v2 plus t2 prime v2 prime. I differentiate this, I get another t2 prime v2 prime, which makes that a 2, plus t2 v2 double prime. Now, let's notice something here. I have certain terms that involve, so I'm going to look at y double prime plus ay prime plus by. Now, I'm adding up how many terms? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I have a lot of things to write down. So some of the terms just involve a T1, not differentiated. T1, T1, and T1. So those three terms, that's T1 times V1 double prime plus A V1 prime plus B V1. That's that. I also have some terms that just involve T2. So here is a T2, here's a T2, and here's a T2. So that's T2 times V2 double prime plus A V2 prime plus B V2. So that's 6 terms. Good. Plus, I have 6 more. Let's see. Here, and well, let me just write them all down, and then I'll collect the terms. So I have 2 T1 prime V1 prime plus 2 T2 prime V2 prime plus T1 double prime V1 plus T2 double prime V2 plus these 2 terms, T1 prime V1 plus T2 prime V2. All right, so I have this and this and this and this. Now, L of V1 is 0. This is 0. And L of V2 is 0. V1 and V2 solve the homogeneous equation. These terms are 0, so they just disappear. So I'm just left with these 6 terms down here. I have the ones that involve let's see. I want to be able to put this together in a nice way. I have this and this. I have T1 double prime V1 plus T1 prime V1 prime plus T double prime V2 plus T2 prime V2 prime. So I just want to keep track of what I have here. T1 double prime V1 prime and T2 double prime V2 prime. T1 prime, that's one of these and one of these. So I also have another T1 prime V1 prime and another T2 prime V2 prime plus T1 prime V1 and T2 prime V2. Now, if I were to take T1 prime V1 and differentiate it, I would get this and this. And if I were to take T2 prime V2 and differentiate it, I would get this and this. So this differentiated is this. So T1 double prime V1 plus T1 prime V1, T double prime V2, right? Plus that, okay. Plus this, let's see, I have, and I do have what? I have a T1 prime V1 and a 2T prime V2. Plus what's left over is T1 prime V1 prime plus T2 V2 prime. And I want all of that to be equal to R of X. Now, if this were equal to 0, and this were equal to R of X, if this were 0, the derivative would certainly be 0. So if I can choose T1 and T2 to satisfy these two equations, I'm done. I'm done. So the two equations I would like to satisfy are T1 prime V1 plus T2 prime V2 equals 0, and T1 prime V1 prime plus 2T prime V2 prime equals R. So think that you're back in high school and you're just solving two equations and two unknowns. This is two linear equations in two unknowns. And what are the unknowns? The derivative of T1 and the derivative of T2. Okay. So let me just write this the way you usually write two equations and two unknowns. Remember, V1 and V2 we know. V1 and V2 are the solutions of the homogeneous equation. So V1 times T1 prime plus V2 times 2T prime equals 0. V1 prime times T1 prime plus V2 prime times 2T prime equals R. So you solve two equations and two unknowns. You get the solution. You can use Kramer's rule or any way you ever learned in, wherever, to solve two equations and two unknowns. You get the derivative of T, T1 prime, is minus V2 R over W. W is the Wronskian. W is W of V1 and V2. That's V1 V2 prime minus V2 V1 prime. And T2 prime is V1 R over W. So we know the derivatives of T1 and T2. So T1 is the integral of V2 R over W dx, and T2 is the integral of V1 R over W dx. Okay. So in the notes, or in the text, this is really just 2 pages, 2.5 pages. But, in a 400 level math class, there's a lot of math squeezed into 2.5 pages. So again, I posted these notes on Blackboard. I also emailed them to you. And you need to, I guess, you need to learn it all. That's the secret. Questions up to this point? So we've now learned 2 things, namely, two big things: how to solve first order linear equations And now how to solve second order linear equations with constant coefficients, homogeneous and non-homogeneous. And the more you study this and the more problems you work out, the better you learn the material. So that's it. Any questions?
I learned for my previous class that method is called the characteristic equation. I don't know, using the Wronskian technique. Also a reduction method, how to reduce from the second order to a first order. And also the integrating factor technique and the separable, how to separate equations, another method.
Right. So separation of variables we haven't talked about yet, and it doesn't apply here. And if you have other techniques as opposed to other language for solving these equations, that's fine. That's fine. You know, again, the characteristic equation for a second order equation is just what you get by replacing the function it's just a quadratic equation. So that's just a word, as an frame. I mean, however so long as you learn the method and to solve the equations, that's fine. And if you've seen this previously in this form or a different form, that's even better because you have a better foundation. Any other questions? Okay. If not, then we are done for the day. And I'll be back here on Monday. Have a good weekend, everybody.
Thank you.
Thank you. Take care.